You're late. Sprinting down the hall, you nearly pass the door to the right room as your shoes screech to a stop. But wait, how did you do that? Although the answer might seem obvious, there's more to friction than you might expect. We can understand it by taking a closer look at a graph of the force of friction in a simple scenario. Let's say you're helping your friend Little Johnny move. Little Johnny wants to move his big box full of furniture, but because of the friction between Little Johnny's big box and the ground, he can't apply enough force to get it moving. Luckily, Little Johnny has many friends to help him apply more force on his box. At first, the box stays still, even as the force increases. But when Giant Jonathan comes along, this force reaches a point called the threshold of motion. Finally, the box starts to move. In this graph, we can see two types of friction. Static friction, when the force pushing the box isn't enough to move it, and dynamic or kinetic friction, which occurs while the box slides along the ground. We can see that static friction is like a ramp. As the applied force increases, it goes in a straight line towards the threshold of motion. Next to it, dynamic friction is a wavy but flat line. Why is that? And why is dynamic friction lower than the threshold of motion? To answer this, we'll have to look a little bit closer. On a microscopic level, we can see that the surfaces of the box and the ground are both jagged and irregular. In reality, friction is the result of these microscopic bumps and valleys getting caught on each other. When force is applied in static friction, it pushes all the bumps against each other until it reaches a great enough force to lift them over each other. After this point, these tiny bumps move across and glide over themselves, still getting caught and creating friction, but to a lesser degree. They aren't as locked between each other as they were when static. That's why dynamic friction is lower than the threshold of motion. There are a couple things that can affect how much frictional force is experienced by an object, however. The mathematical formula that describes this force is F equals mu times Fn, in which Fn represents the normal force to the frictioning surface as experienced by the object, as this force pushes the object and all the little bumps into the surface, making it harder to glide over them. That's why moving the box of furniture was so hard for Little Johnny. Next, mu represents the coefficient of friction, which itself can be affected by factors that change how much contact there is between the minuscule bumps. This can be roughness, shape, or the area of contact. These all participate in how much friction occurs when a force is acted upon by an object. Special thanks to Dion Payne for the wonderful illustrations as presented here. And remember, friction, it holds the world together.